Okay, so let's get started with the next lecture on MOSFETs. So far, towards the end of the last lecture, we had introduced these output characteristics of a MOSFET, where the y-axis is the current, the drain to source current, and the x-axis is the drain to source voltage. And we had chosen different values of gate to source voltage. So here 1.5 to 2.5 and 3 volts are the different values of gate to source voltage. So here we had noticed that the drain saturation voltage, the voltage at which the characteristics saturate, uh, that voltage changes for different values of VGS. And that the reason for that is because VD sat is a function of VGS given by this equation. And as VGS increases, your VD sat also moves more and more to the right hand side. Another observation that we made in these set of characteristics is that the saturation current given by this expression over here, it doesn't increase linearly with VGS minus VT. Instead, it goes as a square, right? You see that the characteristics are fairly closely spaced here, but here they are kind of spreading away from each other. So more or less a square behavior. So if let's say we had for 3.5 or 4 volts, this would have been at an even more higher value. Okay. Okay, let's continue our discussion then. So here I have just summarized the model or the equations for the drain current under linear and saturation regions. So remember that this equation we can choose to ignore for small values of VDS, giving us a nearly uh, purely linear kind of a behavior between the drain current and the drain to source voltage. One important thing to point out here is that once you have chosen a technology, then there are certain parameters that you cannot change or tune for your needs. So for example, in this equation, beta over here is one such parameter, which is a function of W by L and KPN, where KPN itself is a product of two terms, mobility and the areal capacitance. So this thing is fixed. You cannot choose once you have chosen any technology. Even L you cannot play much with. There is a minimum value of L that you cannot go beyond. Okay, what else? Um, Lambda. So lambda is also a fixed parameter, the channel length modulation. Notice the unit of lambda would be volt inverse, right? So as to make this thing as a dimensionless quantity. And yes, another uh, set of fixed parameters, technology parameters are VTH and not, which is the bias independent threshold voltage, gamma, which is the body factor, right? And then 2 phi f, which comes from the bulk potential. So all of these quantities here shown in red are fixed. You cannot change any of these once you have chosen a particular technology. Let's say you have chosen zero point 0.5 micron technology, then we have these standard values. For zero point 0.5 micron technology, we have gamma given as 0.7 volt half, 2 phi f is nearly around zero point 0.7 volts, and like that. You have these are fairly well-known values for a particular technology, maybe zero point 0.5 micron, and we can use them for various numerical calculations in this course. Yes, as I mentioned earlier, that L is usually fixed, whereas you can change W. Okay, you can change VSB, you can change VGS and VDS, but you cannot change these parameters that are shown in red. Okay. All right, so let's spend some time on identifying what region is this transistor operating in. I'll give you a pause so that you can think more about it. What region it is in? Okay, so what is the VGS here? 2 minus 0.5, so it is 1.5, And what is VT? VT is 1 volts. Okay, so definitely VGS is greater than VT, so it is on. It is in on state. And then we have to check VDS, right? So VDS is zero point 0.7 minus zero point 0.5, which is 0.2. Okay, and what is VDSAT? So VDSAT is VGS, which is 1.5 minus 1 VT, right? So zero point 0.5 is your VDSAT. So definitely VDS is less than VDSAT, right? And VGS is greater than VT. So it's an on state, but in linear state because VDS is less than VDSAT. Okay. What about this one? So again, the only difference between these two is that VDS has been increased. Definitely VGS is greater than VT. So 1.5 is greater than 1. So this is an on state. But what about VDS? So VDS is 1 volt. VDSAT is how much? 0 0.5. So definitely this one is VDS greater than VDSAT. Therefore, this is in saturation. Okay. What about this one? Here we have simply shorted the gate as well as the drain terminals together, right? It's the same transistor in which drain and gate are shorted together and the source is grounded. VBS is connected, right? Body and source are grounded, kind of shorted together. So in this case, what can we figure out from this figure? So let's say VGS. What is VG? 2 volts, because this is drain is shorted with gate, so VGS is 2 volts. So VGS is definitely greater than VT, which means that this is on. And what is VDS? VDS is 2 volts. So VGS is 2, VDS is 2, and VDSAT, which is VGS minus VT, is how much? VDSAT is 2 minus 1 is 1 volts, right? VDSAT is 1 volt, so this is in saturation. So this is the typical expression for saturation, right? But one thing, how this one becomes more interesting is because we already have shorted gate and drain together, it acts as if, so this equation will be more useful under this condition. So VGS can simply be replaced by Vx because now it's not a 3-terminal device or a 4-terminal device. It's actually a 2-terminal device, right? Where gate and drain acts like one terminal, source and body act like another terminal. So it's a 2-terminal device in which the uh, current is given by the voltage, the square of this voltage applied across these two. So if let's say Vx is applied here, right? So this Vx is VGS. Okay, so the current will be given by IDS, given by this thing Vx minus Vth whole square times beta by 2. Let's ignore the channel length modulation part for now. So if this is the characteristic of this kind of a structure, so it resembles more or less like the characteristics of a diode, because in a diode you have uh, an exponential kind of dependence on the forward bias voltage, right? If you apply a voltage of V, then you'll have a more or less like an exponential, but the features are similar. Here it's a square, and in some cases people do use this kind of a structure in place of a diode, right? This can easily be used for maybe getting rectification or such applications in circuits. But note the disadvantage is that it's not a strong diode because the dependence here on the voltage is only square, whereas in a real diode the dependence of current on the voltage is an exponential one. Okay, so you can think of this as a diode with a turn on voltage of VTHN, because note this is not just V square, this is Vx minus VTHN square. Okay, okay, another example. So in this case, VGS is how much? 0 0.5 and VDS is 1. So definitely VGS is less than 1 volts. it's less than VTN, so the device is not in on state at all. So it is in off state. So there's no question of checking VDS and VDSAT. So it's simply VGS is less than VTN, therefore the transistor is in subthreshold mode of operation. All right. What about this one? This one, well, most of you might think that uh, this is 2 volts at gate, 1.5 volts at source. So you can say that VGS is 0.5 volts, okay, and VDS is zero point 0.5 volts minus 1.5 volts, which comes out to be minus 1 volt, okay, and so VGS is less than VTN, right, because VGS is zero point 0.5 volts and VTN is 1 volt. So zero point 0.5 is definitely less than 1 volt. So this is in subthreshold region. I hope it's only few of you who have come up with this kind of reasoning, because this is not correct. So why I was trying to just confuse you, and I think the confusion happened because of this arrow. But let me clarify how this works. So what decides whether this one is source or this one is source? So notice that if we have a transistor, remember in the earlier lectures I mentioned that a transistor is a symmetric structure. It doesn't matter whether you apply high voltage here or high voltage here. It's not fixed that this will always be the source and this will always be the drain, right? So let's go back to this figure. So this is at 1.5 volts and this is at zero point 0.5 volts. So certainly current is going to flow from this end to this end. And if current has to go from here to here, then which means, so this is an n-type MOSFET, then electrons have to go from here to here, right, from top to bottom. And if electrons are going in this direction, so this is the supplier of electrons. And what is the supplier? The source. So this is the source, not this one. So in an N MOSFET, the higher voltage value decides the drain, and the smaller value of voltage decides the source in an N-type MOSFET. And it's the opposite in case of a P-type MOSFET. Yeah. So this becomes the drain, and this actually becomes the source. So what is VGS now? 2 minus zero point 0.5, which is 1.5. So VGS is 1.5 and VDS is 1.5 minus zero point 0.5, which is 1 volt. And what is VDSAT? VDSAT is again 1.5 minus VTN, which is 0.5 volt. And therefore VDS is greater than VDSAT. So this is in saturation, not in subthreshold. Okay. All right. So let's take a look at the temperature dependence. Now, often what happens is that MOSFETs or any transistor for that matter, whenever they are used in any application, in any real-time application, they do not necessarily see room temperature while they're functioning. Often you'll see that in your laptops or mobile phones, they get hot because you're running so many applications and your devices are multitasking. They're running at their best capable performance levels. So what happens is that the temperature, the ambient temperature, is not the room temperature. It goes high on the higher side. And what that does is that it degrades the performance of your devices. And that is mainly because of this equation written over here. So so what causes the temperature dependence in MOSFETs? So it's primarily fluctuation in temperature because of this threshold voltage and this parameter KPN. Now note KPN is itself a function of the mobility, right? Mobility of electrons in N-type MOSFETs. So mobility degrades as you increase temperature, right? Similarly, VTN or the threshold voltage also decreases as you increase the temperature. So both of these quantities actually reduce, or they see a decrease in value as temperature is increased. But uh, let's say we focus on this one. If VTHN is reduced, right, as you increase the temperature, then current should increase, because this quantity will increase and the square of that will increase even more. So you will have an increase in IDS. But what if this one is decreasing, right? If temperature increases and this one decreases, then the current as a whole will reduce, because this will reduce, right? So it's not actually fairly obvious as to what should happen to current if temperature was to increase. Let me give you one instance over here. Let's take a look at this one. So if we have a transistor which is biased at 1.2 volts at the gate, and the source is grounded, let's say if the body is also grounded, okay, and this is 3.3 volts, the drain is at 3.3 volts. So the current that is flowing in this scenario is 20.28 microamperes. Okay, so first thing here, the current is in microamperes. Now you'll have to get used to microamperes in case of MOSFETs, right? In MOSFETs, the current is usually of this order, microamperes. Whereas in BJTs, you have the current of the order of milliamperes. So that is one difference between MOSFETs and BJTs. And also note that this 2 by 1, this here represents the W by L ratio. So the gate width to gate length is 2:1. Anytime you see this kind of a ratio written in front of the gate, you can immediately figure out that this is W by L. Anyway, so if we have a condition, this is at room temperature, this is at 25 degrees centigrade or 298 Kelvin. What you have here is that the current is 20.28. Look at this one on the right hand side, that we increase the temperature by 25 degrees. Okay, so now this is working at 50 degrees, right? 50 degrees centigrade. In this case, the current is increasing, right? So if I were to just present this picture, what you would automatically think or reason from this one is that any change in temperature or any increase in temperature leads to an increase in current. Yeah, but that's not true, not always true. Look at this case. Now we are working at 3 volts gate and the source is grounded, and 3.3 at drain. Okay, same transistor, 2 by 1 is the W by L. So this is the current that is flowing at room temperature, right? 0.41 milliamperes. What about 50 degrees centigrade? The current reduces now in this case, 0.39 milliampere, right? The only difference between this case, this scenario on the left hand side and on the right hand side, is that the gate to source bias condition, right? Gate to source bias condition here is just 1.2 volts. Here it is 3 volts. So what we can deduce from this kind of simulation is that if we are operating at a gate to source voltage which is smaller, right? If VGS minus VT is small, okay, so any sensitivity or any fluctuation in VT will be more sensitive. This thing will be more sensitive in comparison to this one, and and it will automatically have an effect on the overall current. On the other hand, if gate to source voltage is high in comparison to the threshold voltage, then if the threshold voltage was to fluctuate by change in temperature, right, then this thing will not change much, right? Because this is anyway very high. Any change here will not be too much or too significant in order to have an effect on the overall current. But in that case, this one will be the more dominant one. Okay, so you can simply infer that whenever we are operating at low gate voltages, right, in that case, the threshold voltage dependence on temperature is a more sensitive factor, right, is a more dominating factor in comparison to this one, mobility degradation. Whereas at higher gate to source bias voltages, this one takes the uh, dominating role. Okay. So far we have discussed the above threshold cases of MOS operating regions. So where VGS was greater than VTN, and we saw linear and saturation characteristics. Now we'll focus a little bit on the subthreshold characteristics. Okay. So you know that under subthreshold that we have the device biased at VGS, which is less than threshold voltage. So here we have a plot of ID. This is the IDS, drain to source current, versus VGS now with VDS of 3 volts. Okay, so we can easily identify from this linear graph that current beyond this point, right? Once we are beyond this point, goes as a square, right? It goes as a square of VGS minus VT, right? It kind of increases in this fashion. Whereas below this point, the current is very small. At least on this linear scale, you cannot see the current at all. It feels as if current is zero, even though it is not zero in reality, but on a linear scale, what you see is that it is fairly negligible and shoots up once it crosses this point. Okay, so we can classify this as the subthreshold region and above threshold region. And notice that this structure or this transistor is biased here in saturation, because saturation, again, we know the condition that VDS should be greater than VDSAT. So VDSAT is VGS minus VT. If VT is 1 volt, you can check that condition that VDS is greater than VDSAT. Yeah, there's one problem with this kind of a figure is that a linear scale does not give you the complete picture. So as I mentioned that the current in this region is very small, and in linear scale it does look like as if the current is zero and doesn't vary at all with V. In reality, that is not the case, because current doesn't immediately go to zero. Notice that this is a log scale where the current is plotted on a logarithmic scale, and every step represents a 10 times increase in current. So here in the sub-threshold region, or the region before the threshold voltage, okay, the current increases exponentially. So it is increasing exponentially with VGS. Even though it is small, it is actually very small in comparison to the on current. It is orders of magnitude small in comparison to this current. But notice that the current here is increasing exponentially. Now, how is it exponential? Because this is a linear graph on a log scale. So when you plot a linear graph on a log scale, it will look like a straight line. So this tells you that the current is increasing in an exponential manner. Whereas on this side, even though the current is more than the subthreshold current, the current is not increasing as rapidly as in this case. Here the current is only increasing as a square. And notice that on a log scale, it looks as if it has flattened. Okay, but so this case, you see that the current is more sensitive. It is an exponential function of the voltage. So this is exponential, and here you can identify this as the threshold voltage. So under subthreshold, you can notice this similarity between the characteristics of a MOSFET and a BJT. Because in a BJT, or let's start with this thing, you see that current is an exponential function of VGS. Here, eta is some non-ideality factor that people often use in order to make their models more realistic. And if we take a derivative of this current, right, a partial derivative, del ID versus VGS, we'll get this kind of an expression, ID by eta VT. Now, what is VT? VT here, please don't confuse it with the threshold voltage. This is not that. This is the thermal voltage. I hope that you're able to recall what thermal voltage means. We have already discussed it in our previous semester when we were discussing semiconductor physics. So Vt is given by Kt by Q. So K is your Boltzmann's constant, Q is your electronic charge, and at room temperature, that is nearly 300 Kelvin, this quantity becomes 26 millielectron volts. And if you divide this quantity by E, which is the electronic charge, what you get is 26 millivolt. So a thermal voltage at room temperature is 26 millivolt. That is what you plug in over here. So one observation that we make from this thing is that in subthreshold characteristics, in subthreshold region, a MOSFET acts like a BJT, because in a BJT, the collector current is always given by this kind of an expression. It goes as an exponential function of the applied base to emitter voltage. Okay, Whereas in subthreshold, the MOSFET current also does look like an exponential function of the gate to source voltage with some non-ideality and dependence on the thermal voltage. Now this IS may not be the same as this IS because it's a different thing. This is a saturation current and this is something else. But focus on this part, the exponential part. Okay, this does look like similar. An advantage in BJT is that the currents are definitely higher. They are far higher than what you usually see in MOSFETs. But on the other hand, MOSFETs do have this advantage that uh, you have a gate that has an oxide or a dielectric between the gate and the semiconductor. So that usually leads to a very high input impedance or an infinite input impedance. So by the way, what is input? Input means the input port because gate to source is the input port and drain to source is the output port. So on the input side you have an input a very high impedance, which is a good thing for your circuit applications. Okay. Now, if we want to run simulations or if we want to use these MOSFETs or any transistor in any circuit application, it has to have a mathematical behavior on a model that can describe its functioning in that circuit. So whenever you use any circuit simulator, for example, you use IC cap or Cadence or Mentor Graphics or any well-known commercial circuit simulator, and if you want to design a circuit using, let's say, MOSFET, a basic 180 nanometer MOSFET, what you'll do is you'll take a MOSFET symbol and you'll drag it from the palette and you'll place it in the schematic, and then you'll add your various components such as the bias sources, the resistances, the capacitances, and other elements. The point being that you can only do this thing if there is a well-defined model of this MOSFET within that tool. Only then you can run a simulation. If there is no such model available, then you cannot do this kind of a simulation. And all of you should understand that state-of-the-art circuit design, it is not like it used to be maybe a few decades ago. Circuits right now are not designed on breadboards, right? They are not designed like in a hit and trial fashion. They have to be done in a fairly sophisticated manner. By that I mean people have to run simulations. There are design engineers who work day and night in companies like Intel or IBM or so many other these EDA companies where they develop chips, and all that work is done using circuit simulators. Now for that circuit simulation, these models are essential. In fact, these are of paramount importance to get fairly good circuit design. Let's so here I will just introduce these models so that you can appreciate their importance. So we can classify these models, MOS models, into two categories. One is your small signal model, and then the other one is your large signal model. So what do we mean by small signal? Is that the model that is developed uh, around a particular bias condition. So let's say we have biased our MOSFET in some condition that we have a fixed VGS and a VDS, and if any small perturbation, any small additional voltage is applied at that bias point. So the model developed around that is the small signal model. Now this thing can further be classified into a low frequency or a DC model and a high frequency or a maybe RF model, depending on what kind of frequency is that perturbation. If that perturbation is a fixed small quantity that doesn't vary with time, then you call it a DC model or a low frequency model. On the other hand, if that perturbation is a wave that has a finite frequency, okay, then it will be classified as a high frequency model. So the same can be applied under large signal. Notice that in large signal the perturbation is not small, it is significantly large. It totally shifts the bias point. Okay, and under this you have whether the disturbance or the shift is a low frequency one or a high frequency one. Based on that, you have these two categories. So let's discuss about the low frequency model. Excuse me. So this is your typical MOSFET, right? As you can easily identify, you have the gate, the source, and the drain, and you also have the body terminal. Now we have these PN junctions formed between the body and the source, and the body and the drain. And so far we have only discussed this structure as a device. And if we have to use it as a model, then we have to understand this as a circuit. We have to understand this MOSFET as a circuit. So we have these four terminals, right? So we what we do is that we simply write down these four terminals. So this is the gate terminal, this is the drain terminal, this is the source terminal, and then we have the body terminal. Okay, let's compare these two. So what do we have here between the gate? Let's take a look at this one. Notice that there is an oxide here, okay, and no current, no DC current flows between the gate and the source, gate and the drain, or gate and the body, because there is an oxide, there is a dielectric here. So the gate terminal is like an open terminal. It's like an open circuit. Okay, there is no connection between gate and any other terminal. So that's done with gate. What about the drain? So there is a current that flows between the drain and the source, right? That is the only significant current that flows between the drain and the source. And between the drain and the body, between the drain and the body, we have a PN junction which is reverse biased, which is shown over here, right? We have this PN junction which is reverse biased between the drain and the body, and between the drain and the source, we have a current IDS. Okay. What about source? Between the source and the gate, nothing, because the gate is isolated. Between the source and the body, we have a PN junction which is reverse biased, this one over here. Okay, and between the source and the drain, we have this current, right? What is there anything else? I think that is it. Yeah, one important thing to note is that IDS, the symbol shown here, is a current source which is a dependent one. This rhombic kind of a figure, this is a dependent current source, voltage dependent current source. And I think that is fairly obvious, because this current depends on what we have, this well-known expression for current. Now IDS depends on, let's take a look at these equations. It depends on VGS, right? It also depends on VDS. So this IDS is a gate voltage as well as a drain voltage dependent current. Okay, and does it also depend on the source to body voltage? So these two equations tell us that IDS depends on VGS and IDS depends on VDS. What about uh, VSB or VBS? Does current depend on this also? Let's take a look. Notice that this threshold voltage is given by this equation over here. Remember the body effect? If VSB is not equal to 0, then the threshold voltage tends to increase as VSB is increased. It's not at the bias independent value. Okay, so this dependence on VSB of this current comes because of the threshold voltage. Because if VSB is non-zero, or let's say greater than 0, then VTHN is greater than VTHN naught, and therefore this quantity will change, and therefore the current will be a function of VSB. So this IDS is not only a function of VGS or VDS, it is also a function of VSB. So therefore making it the overall voltage dependent current source. So this represents the typical low frequency MOSFET model. Now one thing I would like to point out is that this is a very simple model, and it doesn't consider, or it ignores, the resistances at the source and the drain. These are called series resistances. Now notice that you have metal at the top of this contact, right? You have a metal here and you have a metal here. which are basically used to probe or put contacts. And there is this finite voltage drop between the metal and the N plus here and here. And even though it is small, but it is not actually zero. And they do play their role in determining the overall device performance. But for this course, I have ignored those resistances to make it a relatively simple model. Okay. All right. So what is the difference between three terminal and four terminal? So let's take a look at this three terminal or two port structure, which has one terminal which is common between the input port and the output port. I hope you have had some idea about these two port networks in your earlier courses when you read H parameters and maybe ABCD parameters. Anyway, so if this is a unilateral network, a unilateral two-port network, by unilateral I mean that any voltage here, right, at the input port, it has an effect on determining I naught. But the input current, doesn't change if V naught is changed. Okay, let me repeat it again. By a unilateral network, what I mean is that this I naught, the output current, it is a function of both the the input voltage as well as the output voltage. But the input current is not a function of the output voltage. It is only a function of the input voltage. And for such a scenario, simple, if we just sorry, if we linearize this kind of a network. What do I mean by linearize? I think it will become clear in the next few slides. I have an example, but let's imagine that there will be a relationship between I naught and Vi, some relationship, not necessarily a linear one. Okay, any relationship. Let's say I naught is Vi square by alpha. Okay, and let's say I naught depends on V naught also as uh, V naught square by gamma. I'm just giving a square example. Okay, just or V naught by gamma. Let's not square it. So there is some any kind of a dependence between I naught and these two voltages. And similarly, I depends on Vi. So what we usually do in order to draw the small signal model is that we linearize that around the bias condition. So Vi and V naught is, let's say, is a fixed value, and we linearize that. So whenever we have a linear relationship between I naught and V naught, okay, so these two ports, what is the linear relationship between the voltage and the current between two terminals? It's nothing but a resistor R naught. And what is the linear relationship between I naught and Vi? Right? It's also a conductance, right? I naught by V. It's a conductance, but it's a transconductance because it is transferred, I mean, across these two ports from the input port to the output port. That's why we call it the transconductance. So I naught here is uh, it's a function of two things. It's a function of Vi. It's also a function of V naught, and therefore the total I naught can be given as a summation of these two currents. You have this current that flows through this resistance, right? And you have another branch which is a voltage dependent current source. Now Gm is the transconductance times Vi, which is the small signal input voltage. Okay. I hope you are able to recognize the difference between these symbols. So these are capital symbols here. Vi, I naught and V naught. These are capital symbols. They represent the quiescent bias condition. That is the condition, the fixed condition in which this network is operating. And these small symbols, I naught, V naught, and Vi, they represent the small signal perturbation that is added to these quantities. So if you are adding Vi, a small voltage, small Vi is added here, that is the small signal which is superimposed on top of this bias condition. Okay, and it is that small signal behavior that is being represented by this model. That whatever is the change, whatever is the additional current that will result on applying an additional Vi, or an additional V naught. Just keep that thing in mind. Okay, so this is your three terminal structure. What if we have a four terminal transistor or a network? Right? We have one terminal here, one terminal here, one terminal here, and one terminal here. And let's say we have applied V1 here, V0 here, and V2 here. So all these voltages with respect to this point, okay, which is the common ground. I think we can extend the logic that if this is a unilateral network, I naught will be a function of V1, it will be a function of V2, and it will be a function of V0. So the linear relationship, again, we will linearize that relationship, and under small signal, the linear relationship between I naught and V naught will be a resistance. I naught and V1 will be a conductance, a transconductance. Let's call it GM1. And between V2 and I naught will be another transconductance. Let's call that GM2. Okay. And based on that, if we can draw that this small signal network like this, that small signal I naught. Now notice that this is I naught. I naught is represented as a sum of all of these three, right? We have one GMV1, which is one bias dependent current source here. Then we have GM2V2, right? GM2 is the transconductance between this port and this current, okay? And V2 is the applied small signal voltage here, right? Notice V1 is the applied small signal voltage here. I naught is the small signal current that results upon getting these small signal perturbations. Okay, so IDS, the overall drain to source current. So if you want to extend this logic to a MOSFET, so the overall drain to source small signal current is a sum of these three things, right? We have one current that comes because of the dependence of the gate voltage, or the drain current on the gate voltage. The second thing is the dependence of the drain current on the body to source voltage. And the third one is, this one happens because of channel length modulation, right? Because the saturation characteristics are not flat, therefore even VDS does have an effect on determining some fraction of your IDS. And if we have to represent this thing in the form of a small signal network, what it would look like is as follows. So we have the gate, terminal, source, drain, and the body. So between the drain and the source, so these are small signal nodes. Between the drain and the source, we have one voltage dependent current source, which is GMVGS, this one. And VGS is the small signal voltage applied between the gate and the source. Similarly, we have GMB, let's call it body transconductance, right? GMB VBS. VBS is the small signal voltage applied here. And then R naught, which is the output conductance, which goes between the drain and the source. So the summation of all of these quantities gives us the total, the overall small signal current. So this is a pretty balanced or a complete picture of the small signal MOSFET model. Now, earlier I did mention that about linearization. So let's take a look at one example. So how do we linearize some quantity? Now most of you would be wondering, how do we get this GM? How do we get GMB or R naught? And so that we can plug them here and we get the overall small signal current. Let's take a look at GM. Now GM is the small signal transconductance, that is del IDS by del VGS. We take a derivative of the current versus VGS at a fixed bias condition. Now this is fixed, VGSQ and VDSQ. Okay, these are fixed. Okay, what is the equation for IDS as a function of VGS? Let's say we are operating in saturation. Okay, if you're operating in saturation, this is how IDS is expressed in terms of VGS and VDS. Okay, it goes as a square of VGS, right? VGS minus VT square, and it varies more or less linearly with VDS, even though it is a very small variation, but let's say it's there. And if we take a derivative of IDS, a partial derivative, note that this is a partial derivative, versus VGS, what we'll get is this thing. We'll get beta times 1 plus lambda VDSQ. Now note that this is VDSQ, the bias quiescent bias condition. Similarly, we have VGSQ here, okay, minus V threshold, okay. And if we rewrite this equation, we rewrite VGSQ, and we can write this in these two forms, right? GM can be written in terms of the quiescent drain to source current, as well as the quiescent gain to source voltage, okay. So once you know the quiescent operating point of this MOSFET, you can find out the small signal transconductance, GM. All right. So in the same fashion, you can calculate GMB, you can calculate R naught by linearizing, by taking derivatives. Okay. So I've just calculated here these values for you, but I would strongly recommend that you do these derivations at your own places and verify whether these are correct. It will give you some good experience in doing some hand calculations. By the way, what is GMB? How do we derive that? We take a derivative of IDS versus VBS now. Okay, it is versus VBS, and then you will arrive at this thing. Right. Notice that it will have this thing, this dependence on VSB. Okay, so I think I'll stop here, and we'll continue our discussion in the next lecture. Thank you.